Before learning data structures and algorithms, you need to understand one fundamental concept: time complexity. Time complexity measures how the running time of an algorithm grows as the input size increases. Here, the input size is represented by n. It doesn't measure the actual execution time in seconds or milliseconds. Instead, it describes how the number of operations grows as more data is processed. We express this growth using big O notation, such as O of 1, O of log n, O of n, and O of n squared. Understanding time complexity helps you compare algorithms based on how efficiently they scale as the input size grows. Let's start with the simplest. Time complexity. 1. Also known as constant time. An algorithm has one time complexity when the number of operations remains the same regardless of the input size. For example, accessing an element using an array index like R5 always requires just one operation. Whether the array contains 10 elements, 1000 elements, or even 1 million elements, the time required to access R5 doesn't change. Since the number of operations stays constant as the input size grows, the time complexity is 1, 1. Now let's understand O of log n, also known as logarithmic time. An algorithm has O of log n time complexity when it reduces the input size by half during every iteration. A classic example is binary search. Instead of checking every element one by one, it compares the middle element and immediately eliminates half of the remaining search space. For example, if there are 16 elements, the search space becomes 8, then 4, then 2, and finally 1. Since the input keeps getting cut in half, the algorithm performs far fewer operations than a linear search, giving it a time complexity of O of log n. Now let's understand O of n, also known as linear time. An algorithm has O of n time complexity when it processes every element exactly once. A simple example is traversing an array using a single loop. If the array contains 10 elements, the loop executes 10 times. If it contains 100 elements, it executes 100 times. And for 1000 elements, it executes 1000 times. Since the number of operations increases in direct proportion to the input size, the time complexity is O of n. Now let's understand O of n log n, also known as linearithmic time. This time complexity is commonly seen in efficient sorting algorithms such as merge sort, heap sort, and the average case of quicksort. These algorithms first divide the data into smaller parts and then process or merge all the elements efficiently. Because the data is divided log n times, and during each level all n elements are processed, the overall time complexity becomes O of n log n. This is why O of n log n algorithms are much more efficient than O of n squared algorithms when working with large data sets. Now let's understand O of n squared, also known as quadratic time. An algorithm has O of n squared time complexity when it uses two nested loops, where the inner loop runs completely for every iteration of the outer loop. For example, if n is 10, the algorithm performs approximately 100 operations. If n becomes 100, it performs about 10,000 operations. Since the number of operations grows as n multiplied by n, the time complexity is O of n squared. This is why algorithms with nested loops become much slower as the input size increases. Now let's understand O of 2 to the power of n, also known as exponential time. An algorithm has O of 2 to the power of n time complexity when each recursive call creates two more recursive calls, causing the number of operations to grow exponentially. A classic example is the recursive Fibonacci algorithm. As the input increases, the number of recursive calls grows very quickly. For example, increasing n from 5 to 10 results in significantly more recursive calls. Since the work roughly doubles at each level of recursion, the time complexity is O of 2 to the power of n. This is why exponential algorithms become impractical for large input sizes. Finally, let's understand O of n factorial, also known as factorial time. An algorithm has O of n factorial time complexity when it generates every possible arrangement or permutation of the input elements. For example, with 3 elements, there are 6 possible permutations. With 4 elements, there are 24. And with 5 elements, there are already 120 possible permutations. As the input size increases, the number of possibilities grows extremely fast. Since the number of operations grows factorially, the time complexity is O of n, making it one of the slowest time complexities. When calculating time complexity, we follow a few simple rules to simplify the final result. First, ignore constant values. For example, O of 5n becomes O of n because constants don't affect how the algorithm grows. Second, if an expression has multiple terms, keep only the fastest growing term. For example, O of n squared plus n becomes O of n squared. Finally, when comparing algorithms, focus on the growth rate as the input size becomes very large, not on small constant differences. These simple rules make time complexity easier to compare and understand.